Welcome to the Explainer. Today, we're going to tackle a really clever linear algebra puzzle. It's one of those problems that starts with what seems like a paradox but ends with a surprisingly clear, concrete answer. We'll get to connect the super abstract world of vector spaces with the nuts and bolts of matrix transformations. So, this is the big riddle for the first part of our journey today. How can having an infinite number of solutions for one thing and then absolutely no solution for something very similar tell us a fundamental truth? It sounds impossible, right? It's a puzzle that really forces us to look deeper into the nature of the vectors we're dealing with. Okay, let's get into part A. First things first, we need to lay out all the clues the problem gives us. So here's our setup. First, we're told that our main set of vectors, v1 all the way through vk, can span the entire vector space. You can think of this like having all the primary colors. You can mix them to create any other color imaginable. Second, we're told a specific equation using these vectors has infinite solutions. That is a huge clue. But then, for our third clue, if we just take away one vector, vk, suddenly we can't create a different vector w at all. There's just no solution. These three facts are all we have to work with. And here is our mission. We have to use those three clues to prove that the smaller set of vectors, the one that couldn't build the vector w, is linearly dependent. All that really means is we have to show that there's some kind of redundancy, some overlap within that smaller set. So how in the world do we prove this? Well, we're going to use a really elegant and powerful technique, proof by contradiction. It's kind of fun. Instead of trying to prove our statement is true directly, we're going to assume it's false, and then follow that logic until it completely breaks down and leads us to something impossible. But before we dive in, let's do a super quick refresher. What does linearly dependent actually mean? It just means there's some inefficiency in the set. At least one of the vectors isn't really pulling its own weight, because you could already make it by combining some of the others. It's redundant. Okay, let's go back to our first clue. Why are infinite solutions such a massive giveaway? Well, think about it. If all our vectors were perfectly independent, there would be only one unique recipe to create our vector u. The fact that there are endless ways to make it tells you there's overlap. There's that redundancy we were talking about in our set of vectors. And that is the very definition of linear dependent. This slide maps out our entire game plan. So let's walk through it. Step 1, we start by assuming the exact opposite of what we want to prove. Let's just pretend that our smaller set of vectors is actually linearly independent, okay? Now for step 2, we bring in that no solution clue. That clue tells us that the vector w is totally new. It's outside the reach or the span of our supposedly independent set. Step 3, and this is a really key rule in linear algebra. When you take a linearly independent set and you add a new vector that's outside its span, the whole new, bigger set is also independent. This implies that the dimension of our entire space has to be at least k. Now, step 4. Wait a minute. We were told at the very beginning that our original set of k vectors spans the space, which means the dimension can be at most k. So how can the dimension be both at least k and at most k at the same time? Well, the only way is for it to be exactly k. And if that's true, it means our original set, v1 through vk, must be a basis, which means it has to be linearly independent. And that brings us to step 5, the final conflict. We just logically proved that our big set of vectors has to be independent, but our very first clue, the one about having infinite solutions, told us for a fact that it was dependent. Our logic has led us to a complete and total contradiction. So whenever you reach a contradiction like that in a proof, it means one thing: the assumption you started with has to be wrong. Our initial assumption that the smaller set was independent is false. Therefore, the opposite has to be true. The set v1 through vk-1 is for sure linearly dependent. And just like that, part A is solved. All right, now for part B. We're going to take these same ideas about how vectors relate to each other and see how they work in the much more concrete world of matrices and linear transformations. So we're kind of shifting gears from pure logic to actual computation. So our first task is to prove this identity. Now, I know this notation can look pretty intimidating at first glance, but the idea behind it is actually super useful and really powerful. It's all about what a transformation looks like from different points of view, or in math terms, from different bases or coordinate systems. Let's decode this thing. Think of a basis as a language. The first matrix, T from C to B, is like the instruction manual for our transformation T. It's written for someone who gives you an input in language C and wants the output in language B. The second matrix is the same manual, but for inputs in language D. And that last matrix, M, well, M is our translator. It's a special matrix that converts language D into language C. So what is this equation really telling us? It's basically saying that if you want the instruction manual for language C, you can just take the manual you already have for language D and then use your D to C translator matrix first. It's all about chaining these operations together, which is a totally fundamental concept in linear algebra. Okay, time to put this powerful identity to work. We're going to use it along with a few key properties of determinants to hunt down a specific value using the clues we've been given. And here are our clues for this part of the puzzle. We don't know what the full matrices look like, but we do have their determinants, that single magic number that tells us how a transformation scales space. We know the determinant of T from C to B is 3, from D to B is 6, and from D to C is 1. Now, we just have to connect the dots. Let's follow the logic here. First, we take the determinant of our main identity. A beautiful property of determinants is that the determinant of a product of matrices is just the product of their determinants. Easy enough. Next, in step 2, we plug in the numbers we know. 3 equals 6 times the determinant of m. A little bit of algebra, and we find that the determinant of m is 1/2. We just figured out our translator's scaling factor. Now for step 3. We use a second, very similar identity, which you can see right here. We do the same trick again in step 4. Take the determinant of both sides. Then, in step 5, we substitute our known values again. We know the determinant of T from D to C is 1, and we just found that the determinant of m is 1/2. A little more algebra tells us that the determinant of T from D to D has to be 2, and that is the final piece of the puzzle. The determinant of the transformation T itself is defined as the determinant of its matrix when the input and output languages are the same, which is exactly what T from D to D is. And there it is. That's our answer. After all that work, connecting different bases and different ways of looking at the same transformation, we find that the true intrinsic scaling factor of the transformation T is 2. So let's just take a quick step back and think about the big ideas that this two-part puzzle really helped us understand. First, we saw that the number of solutions you have, whether it's none, 1, or infinite, tells you something really deep about whether your vectors are independent or not. We also got a great example of just how powerful proof by contradiction is for finding your way through abstract problems. Then, we moved on and reinforced the idea that change of basis formulas are the secret sauce for translating transformations between coordinate systems. And finally, we saw that a determinant isn't just some random number. It's like the transformation's fingerprint. It's a true property that stays consistent no matter how you look at it, which lets us solve for these hidden values. You know, this whole problem really gets you thinking, doesn't it? What other hidden truths about transformations and vector spaces are just waiting to be found, simply by understanding how they look from different points of view? It just goes to show you that sometimes changing your perspective or your basis is the key to seeing what was there all along. Thanks so much for joining me for this explainer.